Okay, so following along in calculus, in chapter 3, there is a section on related rates when we're looking at applications to the derivative. This is usually a section that causes students a lot of issues. So on top of the textbook work, we have this worksheet that we often work through. So I thought it would be a good idea just to start doing it here too. So question number 1, it's asked about the edge of an expanding cube is changing at the rate of 3 centimeters per second. So this will be, if we're going to say x is the edge, this would be a dx over dt value. When its edge is 4 centimeters long, so then we want to know when x is 4, we want the rate of change of the volume and then the rate of change of the total surface area. So if we start with part 1 or part A, the volume, let's take the first derivative. So the derivative of v equals x to the power 3 would be dv over dt, because we're doing it in terms of time, equals 3x squared dx over dt. So once we've taken that first derivative, then it is an easy plug-in. So we'll plug in the value of 4. So you'd have 3 times 4 squared times 3. So let's go ahead and plug that into our calculator. I just had a different number written down on paper there. So 3 times 4 squared times 3. That will give us 144, and then the units, because we're looking at volume per time, would be centimeters cubed per second. So that's the first one. If we look at B, and it's the total surface area, it's rate of change. So then we're taking the first derivative of A equals 6x squared in terms of time. So you'd have d of A over dt equals 12 times x dx over dt. So once we've taken that derivative. So same idea, now that we have that, we're just plugging in 4. So you'll have 12 times 4 times 3, which ends up being 12 times 12. And we also get 144 here, and this is just coincidence. And your units for this one, because it's area, would be centimeters squared per second. Looking at the next one, similar idea, except instead of finding the volume's changing rate, we are given the volume's changing rate. So we're given a dv over dt value. So it's asking what would that volume's change be if our volume is at 125 centimeters cube. So the first one, the rate of change of its edge, we're looking for a dx over dt, and then total surface area would be your dA over dt. So looking at that first one, because we have that volume, we have that same formula, v equals x cubed. Then we're going to take the derivative, so dv over dt equals 3x squared dx over dt. So in this case, we want to solve for the dx over dt, given that, one more piece of information I'm missing here. Your volume is 125. So we'll have this extra step because we don't know x in this, but if you know that the volume, so it's just coming over here, is 125, right, that's a given, then we can figure out what x is by just taking the cube root of both sides, and we'll see that x equals 5. So now we know the dv over dt, so we can plug that value in. We know what x equals, we can plug that value in, and then isolate dx over dt. And when we do that, we will get, so just plugging in some values, we'll have 10 equals 3 times 5 squared dx over dt. And then dx over dt will equal, what am I plugging in here? 0.13, and the 3 is repeating, and then because it's edge length, it would just be centimeters per minute in this case. If I'm looking at B, total surface area, using that same formula that your surface area is 6x squared, and then taking that first derivative, we'll have dA over dt equals 12x times dx over dt. And we're looking for the same dx over dt. So plugging, oh wait, no, we're not. What is the rate of, we're looking for the dA over dt, the rate of the surface area. So we're finding dA over dt. We know that our first constant is 12. X, we solved that already, is going to be 5. And we actually also solved dx over dt. That's our answer from part A. So we're going to plug in those values, and we should see that our answer here is 7.98, and your units for area will be your centimeters squared per minute. Okay, so those are some of our questions dealing with volume. Our next one, we have a circular plate in a furnace is expanding, so the radius is changing at 0.01 centimeters per second. So this is giving us a rate of change. I'll still call this your dx over dt, where x will be our radius. And it's asking how fast is the area changing if our radius is 5 centimeters. So we're looking at the area of a plate, which is just area of a circle. So area equals pi r squared. And then we want to take the first derivative, so dA in terms of time over dt will equal 2 pi r, and then I'm using x still, but I could use dr over dt, but just because I called it x earlier. So that's what I'm looking for, and now I would want to know this when our radius is 5 from the question. So I'm plugging 5 in here. I also know that I have my dx over dt, so I have all my unknowns. So this would be 2 pi times 5 times 0.01. And when we plug this all in, we should get, and you might see it either with the pi symbol or the pi symbol actually multiplied out and have that decimal. But I have in the answer key here 0.1 pi, and then your units, because it's in terms of area, centimeters squared per second. Okay, another one that does have to do with circles. Number 4, a stone is dropped into a lake, causes a series of circular ripples. The radius of the outer one increases at 2 meters per second. How rapidly is the disturbed area changing at the end of 3 seconds? So in this one, again, we are looking at, which one are we looking at here? The radius of the outer one increases. Is the disturbed area changing at the end of 3 seconds? Okay, so this one is another area question. So area will be pi r squared once again. And because this is talking about the radius, I will use the dr over dt instead of the dx, but same idea, right? And we want to know at the end of 3 seconds. So let's first, and so time is 3. So let's first take our first derivative. So dA over dt will equal pi r, and then dr over dt. So we have that information. The other part that we can take a look at is that we actually can find r at 3 seconds. If we have, and we can use some unit analysis here, if we have 3 seconds and we know it's increasing at 2 meters per second, if you multiply that, it would be at 6 meters for our radius, right? Because this was a dr over dt value. So now that we know our radius is 6, we can plug everything in. So pi times 6 times 2, and oh, I actually forgot my extra value of 2 here when I brought the 2 down. So times one more value of 2, and that's going to equal 24 pi, and then your units, because it's area, meters per second, or meters squared per second. Okay, so now moving down, taking a look, the volume is running from a cylindrical tank 1 meter in diameter at the rate of 3 pi per height. And then this should be meters cubed per minute, where height is the depth in meters of the water in the tank. How fast is the height or surface of the water falling when the height is 3? So with this one, because we're looking at a volume of a cylinder, we do need the formula for volume of a cylinder, which is pi r squared times height. And then notice here that you do have 2 variables, or actually, I'm sorry, 3 variables. You have volume, radius, and height. So we want to use essentially similar triangles, I believe here. Are we doing that here? Oh, not in this one. Oh, we do have the radius. Never mind, I'm sorry. We have the radius. If our diameter is 1, our radius would equal 0.5. So we have everything we need. The next one will be a little bit more, I believe. So let's take our derivative, and our derivative, before we do take it, we'll just plug in a value. So volume will equal pi times 0.5 squared times your height. Now let's take your first derivative. So dv over dt will equal will equal pi times 0.5 squared. And then if you take the derivative of h, it's just going to be dh over dt. So now we're at this point here, but you also were told the rate of the dv over dt, and that's going to be 3 pi times the root of h. So we can replace that part in here. So replacing the left-hand side with 3 pi, I'm going to write h with an exponent instead of the radical, h to the power of a half, and that's going to equal pi times 0.5 squared times dh over dt. So now let's isolate dh over dt by dividing our pi times 0.5 squared to the other side. So that goes away, this goes away, and we'll see that pi value will cancel. And we also, at this point, can plug in the 3 for h. So we'd have 3 times 3 to the power of a half divided by 0.5 squared, and plug that all into your calculator, and you'll see the value 20.8, and your units, because this is a dh over dt, would be meters per minute. Okay. Now this is one where I thought we would be using similar triangles like on the other one, but it's actually for this one. So in this one, if we were to do a quick little sketch, we have a man 2 meters tall walks directly away from a light 5 meters above the ground at 1.2 meters per second. We want to find the rate at which his shadow lengthens. And then it also said, hint here, use some similar triangles and note that dy over dt is 1.2 meters per second. So if I did a quick little drawing here, just in terms of what's happening within the picture, using similar triangles, you have a man who's walking away from the light pole. So if this was our light pole, this side here, the man is walking away from it. And this is 5 meters tall. The man was 2 meters tall. So if we split this man into a triangle, and this distance over here from the light pole to the man, we would say is a distance of 5. And then from the man all the way to the end of the shadow would be our value that we'll call x. So if we use this idea of similar triangles, then if we compare 5 over 2, in terms of our triangle, the value 5 would relate to the triangle y plus x, and our value 2 would relate to the triangle of just x. So that's how we're using our similar triangles. And then we can get our system of equations by making this a little bit easier to work with, where you would have 5x, so multiply both sides by x, and then multiply both sides by 2. So we'll get 5x equals 2y plus 2x. Okay. Now we will isolate x, and when we do that, we'll move the 2x to the side. So you get 3x equals 2y, divide both sides by 3. So our equation here, x equals 2y over 3. And now if you go to take the derivative of this equation, taking the derivative of x will give you dx over dt, and the derivative of 2 over 3y would just be 2 over 3 dy over dt. So we've done quite a bit of work here. Now we can just plug in your dy over dt, which is 1.2 meters per second. So we'll have 2 over 3 times 1.2, right, because your dy over dt equals 1.2. Plug that all into your calculator and you'll get the value 0.8. And because it's just a value of x over t and x was in meters, it will be meters per second. Okay, now we have another one, and these ones are just getting a little bit harder just because, as it does. So in this one, it's giving information. A cruiser is going 30 kilometers per hour, and it's 6 kilometers from a straight beach and moving parallel to it. So if I started with that, if I had, say, a beach, and I'm just going to call this line X, that's going to be the beach shore, and the cruiser is moving at 30 kilometers per hour from it, so 30 kilometers per hour, and it's parallel to this, and the distance was 6 kilometers apart. So that's the first bit. It's asking how fast is that cruiser going to approach a fort of the beach when it's 10 kilometers away. So now how we're going to take this question is that your cruiser, your car, is going to turn. If there was, say, a fort over here on the beach, the cruiser is going to head towards that fort. So that is our triangle, and that is going to be 10 kilometers away. Now, we're going to pretend for a moment we don't know that value just so we can come up with that equation, and we're going to use Pythagorean. So our Pythagorean's theorem, we know a squared plus b squared equals c squared, and in this case, it's going to be 6 squared plus x squared equals y squared. Now that we have that, we can set up our system. The other part is do you know some of these values, right? We know that our y value equals 10, right? And when we plug in our value for y, we can also find out our x value will equal 8. So that's going to matter in a moment. So let's take our first derivative. So the derivative of a constant is just 0. Our derivative of x squared would be 2x dx over dt. And that's going to equal 2y times dy over dt. So we have all this information, and now we can plug in our value. So we do know that when we're plugging in a few, that we're finding dy over dt. Our value here, that 30 kilometers per hour, that's going to equal your dx over dt. So we'll have 2 times 8, right, which we solved for, times 30 will equal 2 times 10 times dy over dt. We'll isolate dy over dt, and you'll get negative 24 kilometers per hour. And we know that value is going to be negative because it is heading towards, not away. Okay, here's our last one that I think also can get a little bit confusing. It's also going to be similar triangles, but we want to use that information. Actually, sorry, it's not similar. It's going to be Pythagorean. But we want to use that information and come up with our picture. So it's telling us your ship is anchored 35 meters is anchored in 35 meters of water, and an anchor cable passes over a fixed point in the bow 50 meters above the surface of the water. The cable is hauled in, the anchor remains fixed at the rate of 36 meters per minute, and then how fast is that ship moving when the cable is from the bow to the anchor 130 meters. So lots of information here, but let's try and start with a picture. So if I drew a very, very simple boat, my boat is anchored into the water. So if we had our water level 35 meters below. So our anchor is starting here, and this distance would be 35. Then on your boat, you're going to have this fixed point, which is 15 meters above the water. So it's connected to your boat. So just pretend my boat's bigger. And it's 15 meters above. That is the point where the anchor gets thrown in, and then we can make a triangle. So we're going to call this point Y for now, and this point X, and we can do the same thing we did in that previous question. We can set up our system. So we'd have x squared plus, and then our other side would be 35 plus 15. So 50 squared equals y squared. And then we can do what we were doing before. We can also solve for our other unknown. If we know that at this point, y is 130, we can solve for x. So we can have, so again, at this point, y is 130. So if we use this formula, we can solve for x. So x squared plus 50 squared will equal 130 squared. So the point we're looking at for is when x is 120. This should have been 50. So we have this information. We'll use that in a moment, but we're going to now take the derivative in terms of time. So we'll have 2x dx over dt. Again, derivative of constant is just 0 times or equals 2y dy over dt. So we have all that information, and now we're going to plug in some values and realize what we're finding. So when it's saying how fast is the ship moving, so if we're anchored in, our ship is moving, it would be moving along the x-axis. So we're solving for dx over dt. So plugging in your values, you have 2 times 120 times dx over dt, and that's going to equal 2 times your y value, 130, and dy over dt, because we know that this value is being hauled in at the rate of 36 meters per minute. That is going to be your dy over dt. Now we'll solve for dx over dt, and we'll see once again we have to imply that negative because it's moving towards its fixed point, and it's negative 39 meters per second. So as always, I hope you find this helpful. That is our last one. If you are following along in calculus, please stay tuned for more videos, and please check out my channel for more chemistry as well. If you made it this far, please subscribe, and if there's any other video I can do for you, let me know. Thanks for watching.